All right, so good morning and welcome to pre-calculus. So this is the first time we're seeing each other, so to speak. If you've gone to the assignment list, I just want to kind of call your attention to this and say I've put things in the folders. I'm trying to add in things like videos here so that if you want to look at all the videos for section 2.2, they're all in here, okay? So all like 11 videos are here. And you can scroll through these or not. These are not assigned. They're not worth points. I'm not giving you points for watching videos. But you are, certainly welcome to watch these. Don't panic when you see week 4. There's nothing in week 4 yet because that's our first test week. Okay, so I'll try to put a pre-test in there, and then we'll do a respondus thing. My heater's about to come on, so that's a Truth of New Mexico there. So there's the weeks that we have tests. Week 8, I don't have anything in there. But week 7, there's something there. And I'll work on getting the videos on there so that you guys can have those as well. So that's where we are with that. Okay. So here we are with week 2. We're doing polynomial functions here. Okay, so I'm just going to go ahead and hit preview so we can see some of the things that we work on. All right. And a couple of things about polynomials is before we get started with the homework for that, I'm just going to kind of go over a couple of traits about polynomials. This will be short, and then we'll just run into doing some problems here. Okay, so go ahead and do that and hit this. So I've got a little pen that I use here. Sorry about my handwriting. I usually talk as I'm doing this. So if you're taking notes on this, you can always rewatch this thing, but trying to take notes off of what I've written is probably not the best choice here. But polynomials, we like polynomials in math because they're fairly well-behaved functions. They're not weird. They're smooth. Okay, they're continuous. There's no breaks. Okay, there's no corners. Okay, so there's never a jagged edge to this thing. There's no corners to this. So what I mean by corner is something like that. Okay, or something like that. That's a corner. Smooth, even at the top, they're going to do something like that. Okay, I mean they might be steep. That's okay, but they're always going to be they're always going to be rounded up at the top and then down at the bottom. And then no breaks. You're not going to see a polynomial. You're never going to have a graph that does something like this. Okay, that would be piecewise function, right? We'll get to those, but for polynomials, we don't do those. Okay, so if you see something with a piecewise function, there's a rule change. That's a piecewise function. That is not a polynomial. It might have polynomial parts, but it's not. Okay. Other thing about polynomials, so they look like, right? So that's p of x. And I'm going to go ahead and I'm going to do this in ascending form, which means we're counting up. Okay, so we're going to say this is a0. You could put an x sub 0, x to the 0 here because that's going to be 1. That's how we look at that. a1, x to the 1, a2, x squared plus dot, 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 right? an, x to the n. Okay, so a couple of things about this. Any of these could be zeros, okay? You don't have to have everything that's on here, right? If I put in x plus x to the 4th, that'd still be polynomial because both my a's are 1s. And they're like, well, what about x squared and x cubed? Well, those were both 0, so we don't write them. Okay, this is finite. Okay, you could have an infinite thing going on here, but that breaks the rules of what a polynomial is, and it turns it into a different class of function. Okay, so we will often write this as something like the sum, right? That's my Greek s, right? That's a sum, and then we have ai x to the I runs from 0 to n. That's what, if you were to type this thing out, this is what you would get. Okay, now your book does not make you do this notation, but every once in a while you're going to see it, and as you go on in math, you're going to see this a little bit more often. So getting used to looking at it is important. but it's not something that you're going to have to be tested on, or you're not going to be like, nobody's going to expect you to be able to unravel this in a moment. Okay, you should start practicing, but you know, you've got some time. I think we're going to get to some of this at the end of the semester too, but you certainly have some time for this kind of notation. Okay, so not as important today or tomorrow, but someday. Okay, so when we look at a graph like this, right, this breaks one of my rules immediately, right? We have two corners. It's like, can this be a polynomial? I'm like, no, it's not a polynomial here. So the graph doesn't represent a polynomial. We're not, oh, I've got to do it this way because it won't let me go forward with the next parts. Yeah. Okay, so we do not have polynomial. Since we don't have a polynomial, because it has, okay, it is not smooth. It's oh, it's continuous. What the heck? Come on, guys. It's not, oh, there we go. It's not smooth. Okay, there we go. All right. And then since the graph is not a polynomial function, we can conclude it is not smooth at, and all they're wanting us to do is to check the thing. It's not smooth at x equals -2. It's not smooth at x equals +2. All right. I won't always do like all of these things, but you know, just to give us some ideas of what they're looking for. All right. So let's see. So they're just asking, you know, like this one, yeah, this could be a polynomial because no breaks and it's smooth. There's no corners, so we're good. They're talking about turning points. Okay, so this n here, okay, this is the degree of your polynomial. Okay, so the biggest power you have, that's your degree. Okay, so n is the degree. And one of the things that we know is you could have at most n minus 1 turning points. Okay, so that means if we had something like this, right, it turned once here, it turned once here. So this could be up to an x to the 3 polynomial. Okay, so this could be x to the 3. Actually, it could be x to the 5th or x to the 7th as well. But I know at least it has to be x to the 3 because we have 2 turning points. Okay, so it can be a bigger one, but they usually phrase it as like, what's the minimum degree it could possibly be? And it's going to be a degree 3. So, you know, if you end up with something like that, right, we're going to have 1, 2, 3, 4, 5, 6, 7 turning points on this. Okay, so degree 8 possible. Again, it could be degree 10 or 12 or whatever, but it has to be at least degree 8. All right. So that's what they're going to ask you for that one. Okay. Let's see here. I want to get to the. All right. That's right. You guys have all taken college algebra. You guys already have all of your graphs that you know. So you know, from college algebra, right? You know what an x to the 3 graph looks like, right? You know that graph looks something like this, right? It could have like actually other humps in here, but this is your basic thing. But all of your odd degree polynomials have this kind of shape. All right, so we could be talking about like x, right, is going to be something like that, right? X to the 3, x to the 5. Okay, we have all right, I'm going to go ahead and look. Okay. No, they don't have to intercept the x-axis. They can, but they don't have to. Okay. I could very easily have written this as a And that would have been just fine as an x to the 3 as well, right? That could be just fine. X to the 5th, though, this could have more, right? This could have a lot more. This could have 4 turning points. And they don't have to go on the line. They could just be anywhere, right? You might have one that touches the line, but 1, 2, 3, 4 turning points. This would be x to the 5th, but this could have been anywhere. One thing that odd degree polynomials do is that they have their end behavior in opposite quadrants, okay? So any odd degree polynomial, okay, so any odd degree polynomial, you kind of have to check out the leading coefficient, right? That's your AN, okay, so that's the leading coefficient. Even though with the ascending form, I wrote this last, okay, it's still the leading coefficient because it's the coefficient next to the biggest degree, right? It's the biggest power of x has your leading coefficient, right? So if your a sub n is a positive number, right, like 1x cubed, 1 is positive, we're going to get n behavior that's going to look something like that. So that's going to be my n behavior. Even if I scooted this off to one side of the axis or the other side of the axis, with a big enough x, you're going to be positive. Okay, with a small enough x, with negative enough x, you're going to be over here somewhere. All right. However, if your leading coefficient is negative, okay, if your leading coefficient goes the other way, then these arrows flip. All right, so these arrows flip. So they, again, this is your n behavior. Okay, this is your n behavior. If your a sub zeros or a sub n's are positive, rather, we're going to be looking at n behavior in quadrant 1, n behavior in quadrant 3. If your a sub n is negative, then we're going to flip, right? We're going to be quadrant 2 and quadrant 4. Okay. So that's odd degree polynomials. Even degree polynomials, right? Their n behavior both goes in the same direction. Okay, so again, if your leading coefficient is positive, we're going to have something that looks like that. Now there might be a whole bunch of little squiggles on the inside here, but in the end, these are both facing up. Just like a parabola, right? If we had y equals x squared, one of the questions that your, I guess maybe 9th grade teacher would have asked is like, which direction does this open? And it opens up. It opens up. The leading coefficient is positive. 2 is an even number. It opens up. And the nice thing about this is once you kind of get this rule, just for a parabola, you've got it for every even polynomial there's ever going to be. Okay, they're all going to look like this. Again, might be weird stuff going on in the middle, but they're all going to be the same. Okay, and then if your again is negative, right? You guys have dealt with polynomials that open down, or parabolas rather that open down. We're going to get something like this. Okay, they don't have to be symmetric. Okay, sometimes they are, but they don't have to be. So you can get some kind of weird thing that looks, you know, something like this, and then maybe it does something like that, and does something. I mean, that still follows all the rules, right? We don't have a corner. We have, you know, it's continuous. So it's just depending on the scale of what's going on here. So you could have a steep thing over here and maybe a not so steep thing over there, and that could happen. Okay, usually with the even ones, they are going to be kind of the same on both sides, but not always. All right, so we'll go into kind of dealing with some problems that they have here. Okay, so they give us a couple of things to figure out, right? They say, well, the graph can represent a polynomial function. Let me ask you some questions about this. Okay, so how many turning points does it have, right? We have 1, we have 2 turning points. So, you know, this could be a degree 3. Okay, let's go down here. The minimum degree is going to be 3. I really wish they gave us a you know, thing to do more than one at a time, but there we go. Okay, leading coefficients. Well, what does this graph look like, right? What does it match to? right? Does it match to the positive ones or does it match to the negative one? It looks like it matches to the positive one, right? The bigger we have for x's, the more positive it gets. That's a positive coefficient, or positive leading coefficient there. All right, so, oh, sorry, this one's opposite. Don't let me get away with that. Okay, that one's opposite. So that looks like our leading coefficient is actually going to be negative. Okay, and the degree is odd. Okay. Sometimes I gotta wonder, it's like, really, they didn't think you thought that 3 was an odd number? Like that was something they had to check on you, huh? Okay. All right. So let me back out of this one more time, because there's one more thing we have to talk about before we get to that question. Okay, the last question. And this is the multiplicity of a 0. All right. So what we have for multiplicity of 0, like say, for example, I asked you to graph something like this. I said, right, we have x squared, and then let's pick a different one, right? Let's do y1 and y2, and we'll say this is x minus 3 squared. So going back to college algebra, do you remember what this 3 does? Okay, that's going to be a horizontal shift, isn't it? So we're going to go, and we can dot in, right, our y equals x squared, right? But we could also, I'll do red, why not? But we can use this to generate what this graph is, right? We just move it 3 to the right, and this is my y is equal to x minus 3 squared, right? So when x is 0, right, then, or x is 3 rather, when x equals 3, then we're going to get a 0 out of this. That's one of the ways I remember which direction this tends to go in. All right, where is the 0? Right, pretend that hits the graph. Okay, so the 0 is over here. And what, just looking at the behavior, right, it kind of looks like it comes down and then it kind of bounces off of the axis. And what we call that is we have a multiplicity of 2. All right. And when you have an even multiplicity for a 0, something like this, then what happens is the graph bounces on the axis for that. Okay. Now, it doesn't have to be like always bouncing up. It could bounce down, right? We could have y is equal to, say, negative x plus 5 squared, right? So just going back and going through all of your parabola stuff, you guys are pros. Okay, so this is a parabola, but it has a shift, right? It has shift 5 to the left. 1, 2, 3, 4, 5. Shift 5 to the left. It opens up or it opens down. Well, in this case, it opens down because we have this negative here. But it bounces at 5. Okay? So let me ask you another one. Go back to blue. Red is stressful. Okay, what if we had x minus 2? Right, that's a y. So this one, right, we have zeros at x equals 0. We have x equals 2. Those are my zeros. 1, 2. All right. So this has a multiplicity of 1. This has a multiplicity of 1. What happened to the graph when it hit a 0 at a multiplicity of 1? Well, it went right through. So that's what's going to happen. Okay, so if I asked you to graph real quick and I said, hey, y is equal to x minus 2 squared, all right, so I can tell what the zeros are real quick, can't I? And now, if I multiplied all this out, I have a quadratic times an x. So my degree here, right, my degree is 3. We have a max of 2 turning points. All right, and if I were to go ahead and just kind of sketch this thing out, right, I know that we're here at 0, and I know that there's a 0 at 2. There's no other zeros, okay? And what this is going to look like, For right now, you're going to have to take my word for it, but we'll get into something a little bit later. But that's what that graph is going to look like, okay? Because we still have, right, we still have the end behavior that has to happen, okay? So we had 1, 0 that had a multiplicity of 1. Oops, I messed up. That was not right. I lied to you. So if you're looking at that saying, wait a minute, that isn't right, you're right, it isn't. So here's my 2. So it goes up. And there we go. Okay, that looks a lot better. Okay, so we have multiplicity, right? 0 at x equals 0, we have a multiplicity of 1. It goes through. Here we have multiplicity of 2, or we have as x equals 0, x equals 2 as a 0, has a multiplicity of 2. That's where it bounces. Okay, so that's that's what the multiplicities mean. Okay, so we go back to looking at our problem here, right? And then they ask about do they have even multiplicity or odd multiplicity? Well, this goes through every time it goes through a 0, right? It goes through. It does not bounce. So we have a 0 at x equals -4, a 0 at 1, -1 rather, and a 0 at 2. Okay. So let's see here. Approximate the real zeros of the function. Determine if their multiplicities are even or odd. So let's see here. We've got a couple of them. We got x equals -4. All right. Oops. The approximate real zeros with oh, okay, wait. I want -4. What else do we have here? We have -1. And we had 2, right? 2. All right, I think that's what they're asking us for here. The approximate real zeros with odd multiplicity are all 3 of them. All right, I fill in empty boxes. What did I not fill in here? I don't want to fill in that one. This doesn't have anything in it. Oh, none. Okay. Oh, this guy's none. Why do they say none? Oh, you know that bugs me. This thing here, this means empty set. I don't know, which automatically means none. Okay, that also means empty set. Don't combine them. Okay, don't do this. This is the set containing the empty set. All right, that's a different thing than just the empty set. And the way I think about it now is it's January, so Valentine's Day is coming. So if you have a sweetheart, you can that's something you have to think about now, right? And if you forget to get your Valentine a gift on Valentine's Day, that says something about your relationship, right? I don't know what it says, but it does say something. If you get your Valentine a gift and there's nothing in it, well, that says something else about your relationship. This just means probably you forgot, which is terrible. This giving you a present with nothing in it, like I really hope your partner has a very good sense of humor and that's the kind of thing you enjoy, or that is going to go south very quickly. So don't, this means a different thing than this does, okay? But yeah, that's what empty set is. So why they made us write in none explicitly. Like, why did you do that? So this was -4, this was -1, and I think 2. Is that, double check that on me? -4, -1, 2, because getting wrong answers on this is awful. I understand that. By the way, if they mark stuff wrong, a lot of times it's because of round off error. I'm sympathetic, but I'm not going to help you with that. You have unlimited attempts, and that's the reason why is that goes. Now, when we get to the test and you have to type this thing off on a test, I double check to see whether or not they counted a round off error properly or not. So, you know, don't panic over the test ones. You know, I'll probably not give you full credit for it, but you know, like I'll do go in and put like a 0.5 or a 0.9 or something like that, depending on how bad it is. So, all right, sketch this function. All right, this is a nice one to go with. It's a good problem. We have a couple of zeros, right? Let me go ahead and write this thing down so we have something to work with here. All right, so we have g of x is equal to, that's great, 1/6. This is just a scaling factor. This has nothing to do with like a lot of what the graph is. All right, has nothing to do with it. So we have an x plus 4, x minus 1, x minus 5. So the first thing we're going to ask, like, what's the degree? Right, what's the degree here? And my degree, right, is I have 1, 2, 3 x's. If I were to multiply this whole mess out, don't do that. If we were to multiply this whole mess out, right, the maximum power we'd have here is x cubed. So our degree is 3. Again, if I were to multiply all of this out, do any of these have a negative x on them? Does this have a negative x? Like, no. All of these are going to be positive x's. So I know my leading coefficient, my an, is going to be greater than 0. Okay, so far I know this is a degree 3. I know that the leading coefficient is 0. Without doing anything else, there's my approximate shape of this graph. Okay, now we have a couple of wiggles in here that we have to sort out. Okay, so what I might want to know are where are the zeros, and all we're going to do is we're going to set this thing equal to 0. Okay, I'll write down the 1/6, but we don't really have to. Right, we're going to set this thing equal to 0, and now you can use your zero factor principle, right? I mean, 1/6 is never going to be equal to 0, so okay, so we don't need that one. You don't have to write that one down. I'm gonna know what happens to the 1/6. Okay, you technically don't have to write these down either, but maybe the first time we do it, we'll write it down. That way you can see where I'm getting these numbers. Right, so we're just taking each of these pieces. They're all times together. So for this to equal 0, any one of these pieces can be 0, and then I'll make that true. So these are the zeros of my polynomial. Okay, so when they're going to ask me to graph this thing, right, I know where the 3 zeros are. Now I don't know where the turning points are. Offhand, that's a calculus question. When you get to calculus, you're going to find out where the turning points are. That's the whole point. That's a giant part of Calc 1 is figuring out where these turning points are. So right now, if you didn't quite get that, as I tell my students in face-to-face, like if you didn't get it, like that's not part of the class that I'm grading you on. They're not going to let you. They're not going to expect you to find out where the turning points are. Okay, they just want to know where the zeros are, and then they want to know like what's going on with the graph here. So the end behavior of the function, right? That's what we're learning here. So what is it doing when it goes to the left? What is it doing when it goes to the right? So when we're going off to the left, it's getting bigger and bigger and bigger, right? As it goes off to the left, it's going up. When it goes to the right, oops, I got my left and my right mixed up. There we go, left to my right, right. And it's a good thing this isn't on the internet or anything like that, right? That could be embarrassing. All right. No, I was right. How am I doing? Sometimes I have to wonder. Up, down, there we go. All right. So end behavior of the function, up, no, down to the left, up to the right. All right, y-intercepts, if there is one. How do you get a y-intercept? Do you remember graphing stuff like this? Excuse me. And what was this called, right? That was your intercept. That was your y-intercept. So when x equals 0, right, y is equal to b. So how do you think we're going to get a y-intercept here? Is we're going to go to this function and we're going to plug in x is 0. So we're just going to set x equal to 0 and see what happens here. So we have 1 over 6. All right, let's see if I can move this over to get the, no, I sure can't. Okay, and then we're going to have 0 plus 4, 0 minus 1. And 0 minus 5. And we're just going to multiply this together, right? This is 1/6. We have 4. We have negative times a negative here, right? Do I really need to write in the positive or write in the negatives here? So what is this? This is 26th, right? 20 divided by 6. And let's see, we can cast out 2, right? That's 2 times 10. That's 2 times 3, get 10/3. So we're 0, 10/3 for my intercept here. 10/3. All right. The real zeros of the function, this is what we already came up with, right? The real zeros of the function, we got that to be -4, 1, and 5. See, they changed the rules on me for college algebra, so I'm not entirely sure sometimes about what you guys know and what you don't know. So I will ask occasionally. So, all right. So here, all right, this one's going to be easy enough to use the pencil on because they're going to be able to grid it for us. 1 and 5. But I have another point, don't I? I have this point. And I'm not going to sit here and try to figure out how to do 0, 10/3. So what I'm going to do is I'm going to hit this window here, and we're just going to type it in. 0, 10/3. And when you do this, don't type in the decimals. Just type in the fraction. Like if they give you some kind of crazy square root, right? Square root of 6 or something, just type in square root of 6. Plot the point, and then we're done with that. And then that's going to be your answer, okay? So if you ever have points that are difficult to deal with, you're going to hit this little box here, and you're just going to type them in, and you're set. All right? So I got my things here, and hooray, we got the whole thing. This is a really good problem. Like if I was going to put a quiz question together, if I was going to put, test 1 together, and I'm like, I need to find a good problem for polynomials. Like this is like my go-to question here, something like this. All right. It makes you graph it, which I think is fantastic. It makes you find the zeros. I mean, there's a lot of things that you have to do to this, and none of them are really that hard, but it does make you kind of tie everything together. All right. So that would be definitely a problem I would pick. This would be another good one. Okay. This one's going to be a little different because notice that the multiplicities, right, they're a little bit more complicated. Okay. So let's go ahead and just kind of draw out what we're going to be dealing with here before we go into it. So that way we have something to refer to. So what was this? This was 0.1. And then we had x plus 1 squared and x minus 3 cubed. All right. So what degree am I dealing with here? So if I was going to multiply all this out, right, this would be an x cubed minus some stuff. This would be an x squared plus some stuff. And then we'd have to multiply this together, wouldn't we? And then we're going to have an x to the squared times x cubed, and that's going to give me an x to the 5th, right? That's going to be a degree 5. Are there any negative parts in here, right? All my x's, right? This is going to be a positive x here. It's going to be a 1. It's going to be x squared, 1x squared times 0.1. All of these are positive numbers. Okay, so my an is greater than 0. Okay, so already, what do you know about the shape of this graph, right? you know that it's going to do something like that because it's x to the fifth, odd degree, and positive number. Okay. How about the zeros? Okay. Well, here we have x plus 1 squared times x minus 3 cubed equals 0. Let's put 1 up there. So again, using zero factor principle, we're going to say x plus 1 squared equals 0, x minus 3 cubed equals 0. And can I go off and say something like x is equal to negative 1, x equals 3? Do we need to go through that and all the detail there? I don't think we do. I think we're okay. By the way, if anybody ever has a question about that, like you can certainly ask that, or if you're embarrassed to do that, you can always ask in the office hours. You can send me an email, say, hey, could you go over this again? And I'm not going to out you. I'm just going to say, well, I've gotten questions about, and we're just going to go through it. Okay, so I'm not going to say, well, Julie's asked about, like, no, not going to do it. Okay, I'm not going to betray you that way. So, so those are our zeros. Okay, what about our intercept? What about the y-intercept? That was when x was equal to 0, wasn't it? So we'd have 0.1. We have 0 plus 1 squared. We have 0 minus 3 cubed. This one's not going to be so much fun. So we have 0.1, 0 plus 1 squared, 0 minus 3 cubed. So that's going to be a 0.1. 1 squared is 1. Negative 3 cubed, that's 27, isn't it? Well, it's negative 27. So 0.1 times negative 27 is negative 2.7. So our y-intercept, 0, negative 2 point. That's why the 0.1 was there, is to make it so that our graph didn't go, you know, all over the place. All right. So that's what we do with that. So it's negative 2.7. All right. So I think that's all the information they're probably going to ask us. All right. But, you know, it's good to kind of sketch it out first so I kind of have an idea of what's happening. I know where the zeros are. I know what the degree is. So let's see what we have here. So end behavior of the function, down to the left, up to the right, same as the last one. Okay. Let's go. Y-intercepts, right? We're going to have one. So this was 0. I'm sorry about always with the interval notation, but your calculus teachers generally really want you to have interval notation like this, so that's what we're going to go with. Find the real zeros. Okay, so what do we have here for real zeros? We had negative 1 and 3. Okay, so negative 1 and 3. All right. And then they're going to ask us to graph the plot. Oh, plot at least 6 points. Oh my goodness, what are we doing here? All right, so we got a negative. Did they give me a pencil? They did not give me a pencil. All right, so negative 1, 0. Plot the point. What else do we have? We had a 3, 0. I'm sorry, yeah, 3, 0. Yep, x was 3, y was 0. Plot the point. We had a negative, we had a 0, and then a negative 2.7. That's what we got for our intercept, right? All right, and now we need some more points. Like I got 3 of them, and we said plot at least 6 points. Thanks. So we got to go through, and we have to get other points here. So we're just going to go through with our little t-table here. Right, we already have, right, negative 1, 3, and 0. So we got to pick some more points. This is completely your choice. All right, it is absolutely your choice. So what do you like? How about x equals positive 1, right? How about that one? So we have 1 plus 1 squared, 1 minus 3 cubed times 0.1. We have to go through and do that. I do not have that sitting up here. If you guys are using a calculator, that's fine. Okay, that's okay. I usually have My trusty TI emulator sitting here, but today I guess not. So this is 2 squared. 1 minus 3 is negative 2 cubed times 0.1. So this is 4. It's going to be negative 8, right? 2 cubed, negative 8 times 0.1. Oops. So it's going to be negative 32 times 0.1, negative 3.2. Okay, so when x is 1, y is negative 3.2. All right, so we have 1, negative 3.2. Okay, plot the point. Oh, wow, look at that. Scale's huge. Okay, how about we try 4? Okay, let's try 4. We're probably going to try 5 too. Let's just go ahead and do that. So let's see here. We've got 4 plus 1 squared. We have 4 minus 3 cubed times 0.1. Well, 4 plus 1 is 5. 5 squared is 25. 4 minus 3 is 1 cubed, 1, okay, times 0.1. So 25 times 0.1 is 2.5. That's not. Okay, so that looks like 2.5 there. All right. So when x equals 4, 2.5. Okay. Where do we go? Oh. Did I tell it to do something else? Oh, it didn't like that at all. Okay. Did I mess that up? Oops, there we go. Come on. 2. Why are you being very difficult with me? 2.5. You're just being extremely difficult. All right. So one more. I don't know why. What did it? So 4. 4, and then 2.5. Right? And we need one more, right? We need one more. 0.5. So we have 5 plus 1 squared, 5 minus 3 cubed times 0.1. Okay. So 5 plus 1 is 6. 6 squared is 36. 5 minus 3, that's 2. 2 cubed is 8 times 0.1. So we have 36 times 8 times 0.1. Oh, that looks delightful, doesn't it? So what is that going to be? That's going to be 240 and 48. So that's going to be 288 times 0.1, 28.8. Okay, so we have x is equal to 5. We have 28.8. Okay. And we'll check. I didn't like it. What did not like? These only integer values of x. Did I type it in wrong? 4, 2.5. I didn't like that at all. We'll check. Okay, we'll just go. We'll know. It'll tell me. You're a terrible person. Okay. All right. Did I mess up my intercept here? No. All right. Well, I messed something up with this. All right. You folks with the calculator will be able to check this a little bit better. But you don't have to connect the points. When you connect the points, Oh, shoot. I don't want to go through the whole thing. What if, can I do this? Oh, I may not have connected the points. You're right. I may not have. I had to hit the little graph button. Okay, that's probably it. Okay, it's not connecting the points on that one. So thank you for remembering to actually press graph. Okay. All right, there we go. So then I have to go through and do it again. We're not going to. We're going to do something else. Yeah. Okay. So there's a lot of these. I don't want to go too long because I know we're scheduled for about an hour, and that's about what we're going to do. So maybe we could do maybe one more to go through all of this. This one doesn't look too bad. Let's see this one. That one looked terrible. Oh, how about this one? This one looks awful. Okay. That one looks pretty good. So what do we have here? We have negative x to the fourth plus 13x squared minus 36. That's our h of x. All right, so in this case, they spell a lot of this out for us, don't they? We have degree 4. We have my leading coefficient is negative. So automatically, I know that. And then I got to factor this, right? Because they're going to say, like, well, first off, what's the y-intercept? Let's do the easy one. Y-intercept, we're going to set x equal to 0, right? So y is just going to be negative 36. So we're going to have a 0, negative 36, yeah? All right. Now, where are the zeros? So this is going to be h of x is equal to negative 1. I am better at factoring, right, if my leading coefficient has a nice number. So all I did was take out the negative so that all of my signs changed. Right? So now I need two numbers that add up to that multiply out to 36, but add up to 13. All right. How about 3 and 12? No, I can't do it. 36 is a lot of numbers. 1, 36, 2, 18, 3, 13? No, 3 and 12. 4 and 9. Aha. Okay. So what we're going to have here, right, is we're going to have x squared minus 9, x squared minus 4. Will that give me a positive 36 and a negative 13 here? Yes, it will. Are we done? Can we keep factoring? Yes, we can. Right? So x minus 3, x plus 3, x minus 2, x plus 2. So now what are the zeros? Right? The zeros are negative 3, negative 2, positive 2, positive 3. Notice they're in order. Some books really like it when you put them in order. I don't think yours really cares. So if you said 3, negative 3, 2, and negative 2, I think your book is going to be just fine with it. It's okay. It's okay. So at least I hope that's what they have. So what's my end behavior, right? To the left, it's going down. To the right, it's going down. Can't screw this one up. Down. Right? Even coefficient, negative, even degree, negative coefficient. What are the y-intercepts? See? Y-intercept was 0, negative 36. All right, the zeros of the function. We had several. We had negative 3, negative 2, positive 2, positive 3. Right. Well, it's 5 points. Hey, look at that. We have 5 points. All right. So what do we have here? We have negative 3. Oops, I need a negative 3, right? X is negative 3, y would be 0. All right, we have a -2, and y is going to be 0. Then we have a positive, I'm sorry, when x is positive 2, y is 0. And then we have a positive 3 and 0. And what was the last one we had? That was my y-intercept was -36. So we have 0 and -36. Plot point. You're not going to get me again. There you go. Behavior is correct. And then, yay, it can be taught. Okay, we got that going. All right, so I'm going to go ahead and stop us here. Okay, I'm going to stop recording, and then I'll ask you guys if you have any questions or anything like that if you didn't want to ask. But for everybody else who's catching this a little bit later, you see something that you're still stuck on, let me know. If you want to see something special, you're like, I'm stuck on this one. Could you go over that? That's fine. So let's go ahead and